We're in part 2 now, page 34, and we're beginning in this chapter on chemistry and biochemistry some ideas about the molecules of life. And I would like to present you with these two molecules actually are of considerable interest to us, because when we metabolize food for energy, we're going to end up with CO2 and water, the complete combustion of a carbohydrate, such as glucose, or starches, which are collections of glucose molecules, will end up, when they are completely oxidized, the end product will be carbon as carbon dioxide, and then we're going to be collecting hydrogen with an oxygen molecule, and we're going to end up with water. This would be the water of metabolism, so to speak. But at any rate, water is also a solvent in which many of the reactions of life are happening, and it's this polar molecule that's of interest to us. So the hydrogen is a very, very small atom and has only one electron that it loses in the presence of oxygen when it covalently bonds, and we have this more or less shape of a molecule. Oxygen has a much larger atomic number than hydrogen, which is only a 1, so something in the order of 16 to 1. And so oxygen actually is much larger than is being depicted here. But at any rate, we get the idea that a water molecule is polar, and this is a partial negative charge over here. It's a little bit hard to make out. Partial negative, and this is a partial positive charge over here. And this has consequences for us. And so with this idea, we're going to come over to this picture here on the next page, page 35, and we're going to consider the idea of hydrogen bonding. And so in physical chemistry, there are the ideas of clathrates, or momentary crystals, in which the molecules, when they're able to freely move in solution, are able to readjust themselves into these momentary weak bond positions, and they take up these positions with a certain degree of force when they're considered in the collective, and the force is represented by surface tension. And you can see that there are species that are light enough and able to distribute their mass well enough that they can literally take a little walk on the water. Water, therefore, has, shall we say, a quality that is not exactly wet. And I want to further demonstrate that. The idea of if you're a child shooting an arrow at your mother's refrigerator, and it has a little suction cup on the end of the arrow, and you've remembered to moisten the suction cup, not dry but moist, and it will actually stick to the refrigerator door. And the reason that it's sticking there is the surface tension of the water is actually creating a hydrogen bond. It's the way we're able, when we're taking a shower, to have our shower curtain actually to a certain degree grip the wall near the shower, and so keep its position. So in that sense, it's very helpful. It's very unhelpful if you're born too young and you have lungs that don't have, how shall I say, this secretion that actually is making things a little bit slippery. And if there's only the water there in the lungs actually pull itself together, and it's very difficult to take a breath in the absence of surfactant. Surfactant is the molecule that allows the lungs to, how shall I say, become more compliant for a newborn child when they're trying to breathe. Okay, so you can imagine if we were to add a detergent to this water right here, the surface of the water would actually relax into bubbles. Okay, because the basically adding a detergent or a soap to a solution of water molecules will basically cover the partial positives and negatives with the amphoteric molecule, and it literally makes water wetter. It will actually relax into bubbles. If you take a look at the detergent in your dish pan, the water has become a series of bubbles now instead of a flat surface, and so the hydrogen bonding is gone, and that's what surfactant does in the lungs. Okay, so as we press on here, I'm not going to be pushing too deeply into the ideas of chemistry. You'll need to take a chemistry course for the purpose of that, but this is just a quick review of the molecular basis of life and some of the things that we will have to study. Acids and bases are definitely part of the program, and it's going to be based to a degree on when water breaks down ultimately, or when there is hydrogen in a large supply. Anything that donates a hydrogen ion like this would be considered an acid. Anything that donates a hydroxide ion to a situation would be considered a base. So sodium hydroxide is a base, and hydrochloric acid is an acid, because they're making contributions of a specific nature in this regard. And we're measuring the amount of, in essence, hydrogen ion in any given situation. So if it's neutral, as is being depicted here, water is neutral, and that's because on average there's only one molecule of water for every 10 to the 7th molecules of water. There's only one molecule of water that will ionize into a hydrogen ion and hydroxide ion. So that's an expression that's telling us that water is a very stable molecule and liquid when it's in liquid form. And so things that are of the neutral persuasion are in this range here, such as milk, blood. Blood has a pH of 7.4. You'll need to know that. It's actually a range of 7.35 to 7.45, but it averages out to 7.4. And so many things in life, whether it's milk, this would be cow's milk rather than a human mother's milk, but in either case, we're going to be feeding our children that are infants, newborns, milk, because we're a mammalian species, and it's going to be neutral. And then things become a little bit more, in this range over here, we're becoming more acidic, and basically the pH changes. When we get down here into this range, we're getting into the acidity of the human stomach in gastric juices, and that actually is in excess of what we would experience with lemon juice. And then up in the other direction, we have things that are household bleach or soapy types of products. Okay, so ultimately the human body in most of its presentations outside of, shall we say, the stomach and the small intestine. The stomach has a pH of 2, and the small intestine has a pH of 8 or 8.4, somewhere through there. So the rest of the body should be maintaining somewhere in the vicinity of a neutral to a blood-related type of pH. Okay. There's going to be buffers that we'll be considering, but we'll press on here to consider just actually the molecules themselves that are commonly found in life. And so in this case, we're going to be looking at carbohydrates, and we'll be taking a look at individual sugars, for instance, glucose and fructose, individual sugars. Galactose is one of the sugars that are put together. When put together with glucose, forms milk sugar. This is the common table sugar, which is a disaccharide, as you can see here, which is sucrose. Okay, so glucose and glucose is maltose. And this is a much more neutral, energetic type of sugar molecule, and it's what's broken down from carbohydrate ultimately. When we have more than two of these together, we call it a maltodextrin. Okay, galactose is the milk sugar. Okay, and so we'll carry on from there in our next episode.